Hi everyone, today we're diving into some foundational and future-oriented aspects of computer engineering, from chip manufacturing and why chip making is so hard, to photolithography and CPU production, and even the future trends for engineers. Each of these topics is a piece of the bigger picture of how technology shapes the world. Let's begin with chip manufacturing. Chips or integrated circuits power nearly every digital devices we use, from our smartphones and computers to cars and even household appliances. These chips are made from silicon, a material that's highly abundant and a fantastic semiconductor, allowing it to conduct electricity in controlled ways. The manufacturing process starts with extracting pure silicon from sand. This pure silicon is melted and then cooled in a controlled environment to form cylindrical crystals called ingots. These ingots are sliced into very thin discs called wafers, which form the base for building multiple microchips. To build the layer of a chip, manufacturers deposit thin layers of materials like silicon dioxide on top of the wafer. This helps to insulate the components and create pathways for current. So next is photolithography and patterning. We will get into photolithography in more detail soon, but essentially this step involves creating detailed patterns on each layer. These patterns guide where transistors and elements will be placed, allowing each layer to work as part of a functional chip. Etching removes unwanted materials to leave only the desired pattern, while doping modifies parts of silicon to either attract or repel electrons. This creates the positive and negative regions that enable transistors to control electrical signals. Finally, every chip must undergo rigorous testing to ensure it works, and if a batch has defects, it could lead to costly delays or shortage. This process is incredibly intricate, with each step needing absolute precision. Even a small speck of dust can ruin a wafer. And this attention to detail is part of what makes chips manufacturing both challenging and costly. As I think about the intricate details of chip manufacturing, it makes me appreciate how engineers have essentially redefined what's possible at a molecular scale. The amount of innovation packed into this process is incredible, and imagine working under extreme condition handling pure silicon in such controlled environments, or developing fabrication facilities that cost billions of dollars just to keep up with demand. I think this highlights something essential about the field, which is the computer engineering is as much about persistence and resilience as it is about technical skills. There is this constant push to do more, to make technology smaller, faster, and more efficient, and that drive is inspiring. Now that we understand the basics of how chips are made, let's dive into why this process is so challenging. As technology has advanced, the demand for more powerful and efficient chips has skyrocketed. But making smaller and faster chips comes with serious obstacles. Engineers are working at the nanoscale, where even the tiniest error can result in major malfunctions. As we try to fit more transistors on a chip, we hit physical limit with silicon. Shrinking transistors means they start to experience problem with heat dissipation and energy efficiency. Additionally, signals can begin to interfere with each other at smaller scales. This is one reason why for a while Moore's law, the idea that chip performance would double roughly every 2 years, is slowing down. Silicon is nearing its physical limit in terms of how small we can go. Researchers are experimenting with other materials like graphene, which promises better performance but brings new manufacturing challenges. It each alternative materials requires different production methods and poses unique challenges for durability and cost. Scaling production is another huge hurdle. Creating one perfect chip is difficult enough, but manufacturing millions consistently without flaws requires immense precision, quality control, and advanced machinery. This is why the cost of building a modern chip factory or fab can run into billions of dollars. All these factors make chip manufacturing one of the most complex industries out there. It's a balance between advancing performance and maintaining reliable production at scale. One of the biggest takeaways for me was understanding the impact of miniaturization as we try to fit more power into smaller chips. We directly influence the device that run our lives, our phones, laptops, and even the sensors in cars and healthcare. The impact is fast on a personal level. I think this pushes me to think more critically about sustainability and how can we continue advancing without putting too much strain on resources, both natural and human. These processes are costly not just financially but also environmentally, and they bring up question of resource management and ethical responsibility. Speaking of intricate processes, let's look at photolithography, one of the most critical techniques in chip making. So, photolithography is a key process in chip manufacturing where light is used to create extremely fine patterns on the wafer. Think of it like using light to print a design onto each layer of the chips. Photolithography enables us to create the complex networks of transistors and connections within the chips. So the process begins by coating the wafer with a light-sensitive chemical called photoresist. A pattern is then projected onto the wafer through a mask, which serves as a stencil for the desired layout. So when the light hits the photoresist, it hardens in certain areas and stays soft in others, creating a pattern that will be developed and etched. So to continue making smaller and more powerful chips, the industry has turned to extreme ultraviolet lithography. This technology uses incredibly short wavelengths of light, which allows for even finer patterns. However, EUV machines are among the most expensive pieces of equipment on the planet, costing hundreds of millions of dollars each. So, why photolithography matters? Photolithography is at the heart of manufacturing chips. By creating finer patterns, we can fit more transistors on a chip, boosting its powerful and efficiency. And it's one of the reasons why our devices keep getting faster and more powerful. Photolithography is almost poetic. The process requires this balance of science and art, where you're using light to build structures at an unimaginable scale. I think this process reflects one of the most beautiful aspects of engineering. It's not just about the outcome, but also about the mastering each step. To me, photolithography is a reminder that there's an art of to precision, and that every line and every layer has to be exact for the chip to work properly. It's almost like an invisible artist work behind every device. This reminds me that while engineering is often seen as purely scientific, there's also a layer of creativity and artistry in it. So now that we know how photolithography plays a role in chip design, let's talk about how CPUs, the brain of our computers, are made. CPU or central processing units are often called the brains of computers because they execute instructions that allow programs to run. CPU are built using the same steps we covered, starting from silicon, using photolithography, etching, and layering. Each CPU bit starts with a carefully planned design. Engineers map out every single component on the chips, billions of transistors, pathways, and connections. Modern CPUs contain billions of these transistors packed into a smaller area than a fingernail. This design process is a feat of engineering, balancing speed, efficiency, and heat management. Once the CPU design is finalized, it's fabricated on a silicon wafer using photolithography and other techniques. Other productions, CPUs go through extensive testing. Each chip is checked for performance, energy consumption, and durability. Those that don't meet high standard may be downgraded or discarded. While CPUs handles countless tasks in our daily lives, every time you open an app, browse the internet, or play a game, the CPU is processing the data behind the scenes. The efficiency and power of CPUs direct affect before uh, performance, battery life, and user experience. Producing a CPU showcased that the best of computer engineering from initial design to the complex manufacturing process. It's incredible how much power is packed into such a small chip. CPUs are such a crucial part of modern technology, and learning how they're made has given me a new perspective on their complexity. It's incredible to think that every function of a computer, from simple calculations to rendering graphics, happens because of billions of microscopic transistors working together seamlessly. I realized that CPUs are not just hardware, they're just result of well-orchestrated design process that involves rigorous testing, collaboration, and innovation. Knowing goes into making a CPU reminds me to value these tiny components that drives our world. They represent the best of human innovation and teamwork. The global chips shortage showed us how much we rely on these tiny components and how vulnerable the industry can be to supply chain disruptions. This makes me think about the responsibility we have as future engineers, not just to innovate but to ensure stability and accessibility. The way forward may evolve balance between advanced tech and sustainable, scalable process that can meet demand without causing shortages and or increases costs drastically. With that look of CPU manufacturing, let's consider what the future holds for computer engineers and what technologies will shape our careers. Learning about future trends in computer engineering felt like getting a glimpse into what could be the next big thing in technology. Technologies like computing and AI are not just advances, they're paradigm shifts. Quantum computing, for instance, has the potential to solve problems we can even dream of, tackling with classical computers like simulating complex chemical reactions or optimizing large-scale logistics in ways that could have changed entire industries. But as amazing as these advancements are, they also challenge us to constantly learn and adapt. It makes me realize that to thrive in this field, I need to stay curious and open to continue learning. The topics in the video helped me to clarify my own values and vision for the future. The field of computer engineering is vast, and it's more than just solving technical problems. It's about considering the societal impact, ethical responsibilities, and sustainability of the solutions we create. Going forward, I want to focus on building technology that respects these values, whether that means designing hardware that conserves resources, contributing to secure data management, or advocating for ethical AI practices. These topics brought me to a deeper understanding of what it means to be an engineer. Every chip, every CPU, every new technology has a real world impact. Engineers shapes the tool that shape society, and that's incredible. It's a reminder that the work we do isn't just technical, it's meaningful, and it has lasting implications. Whether it's creating more powerful CPUs, protecting data, or advancing new fields like quantum computing, our work is about improving lives and making the world a better place. As I look ahead, I'm excited about the opportunities and challenges in computer engineering. The journey will involve technical learning, ethical consideration, and creative problem solving. These reflections remind me to always stay grounded in the values of curiosity, responsibility, and innovation.